Good afternoon. All right, let me get set up here. Okay, so first of all, I visit a lot of countries. I've spoken at a number of Go conferences, and I want to say that I love coming back to China because I haven't found a larger, more vibrant community of Go programmers than right here in China. So thank you very much for having me back. So when Astra and I were talking about coming to Beijing to give a talk, I asked him what Chinese programmers were interested in. And he said that testing was always a popular topic. And that was really good because I've been the technical lead of a product for about a year and a half now, and I think about testing every single day. It's something that preoccupies me as the architect. So with that, what I want to do is today we're going to talk about how to test, what to test, and perhaps most importantly, why. Why should we test? Now, there's probably a wide range of experiences in the room. We have very experienced Go programmers through to people who might be just discovering the language today here in this room. So I thought that I would start by giving a tutorial on how to write a test. So let's say we have this function. It's a simple function that takes a string and splits it. It's not very big. So how can we go about writing a unit test? Writing a unit test starts with a new file in the same directory. And a test is just a function, just a simple function. We have some inputs, and we compare it to what we're expecting. And if they're not the same, then we give an error. Now, as I said, tests are just regular Go functions, but they have two rules. The first rule is that it has to start with test, capital T-E-S-T. The second is that it must take one parameter. It must take a testing.t. And the T is a type that's injected by the testing package, and it gives you the ability to print, to skip the test, to report errors, and ultimately fail the test if you need to. So because test functions are just regular Go functions, and they're capital, so they're capital T, we don't want them ending up in the public API for our package. Instead, we only want to compile them when we're running tests. And to do this, the Go command understands that this is regular code, and anything ending in _test is a test file, and so we'll only compile them in test scope. So now we know that a package and its tests live together. So now we have a function, we have a test. How can we run them? We do that simply by typing go test. It says pass. Didn't take very long. If you have many packages in your project, this is from the project that I work on, you can pass /.. or some names or some relative path to say run the tests here. And so you can run all the tests at once if you like. The next question is, well, what about code coverage? Luckily, the Go tool has built-in code coverage, and we invoke it just like this. Go test, just like before, cover profile, and we give it a name of a file to put the coverage in. Now, it prints out helpfully a summary of the coverage and says we have 100% here. And that's not really surprising because this isn't a very complicated function. If we want to dig into the coverage, we have a second tool, go tool cover, and we give it the file that we just made. And it will break down by function the coverage for each function. Now, I mean, this isn't a very exciting example. It only fits on a slide, but you can imagine for the code that you've written, many functions, many packages, this is quite useful output. In fact, this pair of go test, go tool cover is something that I use so often. I've written a little bash helper that I can just run, just type cover, anytime that I need to check the coverage of a package. If you want to explore your code's coverage, you can do so with a HTML report. And again, we just run go tool cover in HTML mode. And we get a nice little web page which shows us green, the code that's covered, red, code that isn't, and there's a little pull down where you can move between the files in the package. So this is all very useful. So, we wrote some code, we wrote a test, we got 100% test coverage. Done, right? That's it. I'm off. See ya. Who thinks that's all there is to it? Even though we have good branch coverage, we probably need to test some boundary conditions. For example, we test that we can split on slash, but if we want to test splitting on a different separator and see what that does, we write another test. And say we wanted to test what happens if there is no separator at all. We write another test. And that's all great. Like, we're building up good boundary conditions. We're testing with adversarial input. So that's good. But you know, this isn't too big. But the problem here is that all of these functions are the same. The only thing that differs is the input, the output. It's all the same. Oh, and the other thing it changes is the name. So there's a lot of boilerplate there for input, output, and the name. What we'd like to do is set up these inputs and these outputs and feed them to a test harness. And so this is a great time to talk about table-driven tests, which is really what I'm here to talk to you about. Let's take a quick look at the structure of a table-driven test function. It's a test. We have a type at the top to hold the inputs and the outputs. And then we build our test cases one at a time, just specifying the input, the separator, and what we expect. And down at the bottom here, we loop over our tests, and for each of them, we pass the input, we check the output, and we check that we got what we expected. So now we've taken that very large function that had a lot of extra boilerplate and made it into something like this. In fact, we can even make it more compact by writing it like this. We declare an anonymous structure and initialize it all in one line. So this and that are pretty much the same. They do the same thing. Perhaps you can even eliminate the names of these fields if you want, but I wouldn't recommend it because that means that you always have to supply these parameters every time, and it does get a little hard to read. So now we have our testing framework, or at least our test harness for the split function. We can say things like, well, what happens if the string we're trying to split has the separator at the end? Well, it's very easy just to add an extra line here, and now we have a full test for that condition. every time you can think up a new kind of input, you just have to add an extra line here. And when we run the test, we find that it fails. Okay, test fail, that's okay. But there's a few things to talk about here. The first is, by rewriting those individual test functions into a table-driven test, we've lost something. We've lost the name of the test case. I mean, there it is, it's there in a comment. But comments don't exist at compile time. Now, there are a few ways that you can resolve this, and you'll see these styles in various code bases, because this style of testing, this table-driven style, is very much something that is still evolving. We're still learning how to do it better. Now, as our tests are stored in a slice, we could print the number, like the index of the slice. We could say we're testing test number 1 or test number 2. So we could do it like that. And then when we run the test again, it says test case number 4, expected this, got that. This is okay, but there are a few problems. Slices start at 0, not 1. So we have to kind of fix this here. We have to remember to add 1, so it is a human number, not a computer number. And that requires consistency. Everyone has to remember to add 1 or not add 1, depending on what the policy is at your company or in your code base. And more importantly, if this list of test cases is very long, and they're probably much bigger objects, finding number 4 in that list might be a bit hard. So we can probably do better. Another common pattern, because we're defining a structure to hold our test fixture, we'll just put a name field in there. And then at the bottom here, we can say, we say the name of the test case that we're running. And that's better. Now we have the name of the test that failed, and it means that we can go back when we're trying to fix this and say, oh, this is testing SEP. That's the one I'm looking for. So that works well. And the good news is that we can actually improve this further. It turns out we can drive this up even more if we use a map. So instead of declaring a slice of structures, we use a map of structures. The key in the map is the name of the test, and the value is the actual test fixture. The rest of this is pretty much unchanged. But now apart from making this a bit nicer, moving the name outside of the test case, there's one other big difference that doing it like this rather than a slice does. Can anybody think of the reason why? I'll give you a hint. It's something about the property of using range over a map. So just yell it out. Okay, I think I heard the answer. That's absolutely right. Map iteration order is undefined. Some people say it's random. It's the same thing. The order in which we loop over these elements is not that order. It's random. And this is very, very useful for making your test case more robust. If you have two tests that only pass when they're run in order, A works and B works, but if you reverse the order, they fail, or if you try and run B without running A, it fails, that's a sign that your functions are not hermetic, that they are changing some global state. And the fact that the tests work is only because the second test that runs is actually depending on the behavior of the first one to change the world around it. So it's excellent to find these problems and root them out. And by running your test cases in an undefined order is an excellent way to do that. Okay, you'd think we'd be finished, but there's still more to talk about. Before we actually fix the test, there are two other problems with this test harness. Can anybody think what they are? I'll give you a clue to the first one. It's this. T.fatalF will terminate the test function. That means the first error we find working through our test cases, the test will report it, and then the test will stop running. Now, this means that because our tests are running in a random order, if there's more than one failure, we may only get the report of the first one. And then we fix that, we run our tests again, and we're like, oh, there's another failure. If you're working in an incremental mode and you're adding one test case at a time, it's likely that you're never going to have more than one broken test case at a time. But if you're refactoring or you're doing some work to the internals of the function under tests, it's possible that you could break every one of these test cases. And writing the test like this means that you're only going to get one report. You fix that, you get another report. You fix that, you get another report. What we would like is for, if there are multiple failures in this set of test cases, that we get them all reported at the same time. So one way we can do this is, rather than calling fatal, we'll call error. So error marks the test case as failed, but it continues execution. And for a simple example like this, that's okay. But you can imagine if for each test that you needed to run, you needed to have several checks. If the first one fails, it's likely that the second one won't be possible. You won't have the right information. Like, say you needed an object from the first one, and if that was an error, then you couldn't continue. And so the problem with using error-F is that it means that you have tests that work very well when all the test cases pass, but they tend to, when a test case fails, that causes them to not just report the error, but maybe nil panic or crash or something like that, because what happens if this didn't work and we continue on path is not generally well tested. And this problem comes from the fact that we used to have one test per function, so we could abort each different function independently. Now we've merged them all together, we've lost that behavior. But the good news is there's a solution for that. Go 1.7, which is 3 years old now, added a thing called a subtest. And I'm going to show you how subtests improve this table-driven testing methodology a lot. So here is the same function that we saw before, but we're using a subtest. And a subtest is simply calling t.run, you give the test a name, and you pass it in an anonymous function, which is the body of the test. So because it's now inside its own function, you can go back to using fatalF. And you can be sure that when this happens, it just terminates this function, not the whole test. Another really good benefit of subtests is that the tests have really good names. It's right there. The failing test is test split, trailing separator. You can see it. It came from this input. So we get a good name, We get reliable T-dot fatal behavior. It also means because these tests have names, you can run them individually. Previously, all we could do was run all the tests in for a split. We couldn't say just run one of them without going in and commenting the others out. Now they have a name. You can pass this regex that says run the trailing separation test only. So now we're ready to fix the test case. Finally, we're finally ready to fix the test case. We expected ABC. We got ABC and some space or something like that. Obviously the problem is here. There's something here, and that's why the expected and what we got are not the same. But what is that? Like, it's just a blank space. One way we can improve this output, give us a better chance, is to move from using %V to %V. And this is an extra formatting tool that the format library supports, which says print this out in Go syntax. That's what we say. So now when we run our test, it says, I expected a slice of strings, A, B, and C, but what I got was a slice of strings, A, B, C, and a blank space. So that's great. That's helped us understand. We know that our test failed, but it's given us a clue what the actual problem is. Something in splitting that string is putting an empty space at the end. But I want to advise a little bit of caution here, because our split function is very simple. It works with primitive strings. Most of the time, the tests that you're writing are going to be on more complicated objects. So I want to show you the limitations of using %V. This is a very simple function. We have two slices, one of a pointer to a T of 1, a T of 2, and a T of 3. So T.I is 1, 2, and 3. And here we have pointers to 1, T of 2, and T of 4. Now, so that you can understand this, I'm going to print out the %V version and the %#V version, so we can compare them together. Now, as you expect, %V isn't very useful because it's not printing out the numbers 1, 2, and 3. It's getting confused by the fact that these are pointers, pointer types, not values. So it's just printing out the memory addresses. And similarly, %V, well, it tells us how to make the type main.t pointed to a main.t, but it doesn't tell us what's inside that. It just tells us the memory address. So %#V is probably not going to be that useful for us for general advice. Now, the problem of printing complicated Go structures is not a new problem. There are dozens of pretty printers. PP is very, very popular. Go Spew has been around for a long time. But the one that I want to talk to you about is Go CMP. Go CMP is written by a Google engineer, Joe Tsai, and he gave a talk about it at GopherCon about 2 years ago. This is what it looks like. I'm not entirely sure why I included this slide other than it's on GitHub. So the goal of the compare library is obviously to compare two values, just like reflect deep equal, but it has many, many more features in terms of how it does that comparison, what it will accept, and most importantly for us, how it presents the difference. So this is the same example as before. And if we were to use compare.equal, it's just going to say they're false, just like reflective people would say it's false. But more useful is this amazing diff function, which is going to tell us if there is a difference between these two objects, what that is. So let's run this and we'll see what it looks like. And it tells us in a kind of, sort of like a diff style, like it says, at the second index, so 0, 1, 2, the second index, the field I expected it to be 3, but it was actually 4. It's told us exactly where the difference was. It hasn't just said they're not equal. It has told us why they're not equal. So I don't really have time to talk more about this other than we're just going to use it. But do look into the compare library. It's a really, really useful tool. So let's feed that back into our test case. I've written this on 2 lines, just so it was shorter, but you can write it on 1. And we're basically saying, let's compare what we wanted with what we got. And if there is any difference, so basically if the string is not blank, if there is some difference, then we're going to fail and print out that difference. So now instead of this, which we had before, we have this. I'm just going to go back and look at how much we've improved the readability, the usability of this test case. Previously it just said, I wanted an A, B, and C. I got a different A, B, and C. That's all it said. Now, the test has a name, and it tells you exactly what happened. There's an extra element in this string. I don't understand why there's 3. 3 shouldn't be, the third element shouldn't be there, but it was, and it was empty. So it's told us exactly what's happened. So now we can fix our split function to deal with this trailing separator. We can just patch it up, it's fine. And now our tests pass. That's great. Let's check our coverage. Make sure we haven't introduced any uncovered branches in this new code. Nope, it's looking good. Still have good coverage. All right. Okay. So we talked a little bit about how to write a good Go test. The next thing I want to talk about is what kinds of things we should be testing. How should we choose what parts of our code to test? Should we just test everything? Test absolutely everything? Should we do that? Perhaps a different question to ask is, how should we choose when to write a test? Should we write our tests after we write our code? Maybe somebody else writes them. Maybe the QA group writes them. Maybe the people who are integrating with your service write them as a kind of verification. Maybe. Maybe we should write our tests beforehand. Maybe the architects should write all the tests for our code, and then we just write the code to make the tests pass. Maybe. My answer is that we, you and I, all our software developers, should write test cases at the same time as we write our code. Does anyone know what this practice is called? I think I heard a murmur of it. So yeah, this is test-driven development. And it's complicated. It's got a complicated relationship. It's complicated. So can I do a little poll? Who likes TDD? Can I just put up your hand if you like TDD? Whoa, this is going to be a tough room. It's like 3 hands. Okay, who doesn't like TDD? Put up your hand. Well, okay, so the people who do like TDD are winning by 2. Okay, so for everybody else, I'm assuming that you're like me and you've tried TDD, you want to like it, but there have been some problems. You've hit some roadblocks. I believe that TDD is the right way to write software. Doing your testing after you've written your code, that's so waterfall. It's so 1990s. It's just that applying the ideas of TDD that I was taught always seemed to be really hard. But the point is that I hold as an article of faith, I believe this, that writing tests at the same time as writing the code is a good thing. Now, the thing about me is that I don't have a software engineering background. I grew up as a system administrator, a DevOps, an SRE. And so I came to software development very late in the picture. And this is how I learnt about TDD. I saw a presentation by Robert Martin, and he talked about the 3 rules of TDD. And there are 3 rules. The first one is that you're not allowed to write any code unless it's to make a unit test pass. The second one is that you're not allowed to write any more of that unit test than is sufficient to make it fail. And the third one is that you're not allowed to write any more code than is sufficient to fix that one failing test. So when you take these three rules together, and this is Martin's argument, you have this very tight loop that if you want to implement a function, you write a test to call that function. That test is going to fail because you haven't written the function yet. So how do you fix that? You apply rule 3. You just write the function, takes nothing, returns nothing, but it makes that test pass. So the next step is you want to make the function actually do something. You change your test to pass an argument and expect a response. And again, you then have to fix the code to match the test. And this all sounds really sensible, because at the end of the day, if you are following this practice, it means that at any time, if your tests break, all you have to do is Control-Z or git revert. Just stash the latest working copy, and you're back to 100% of your tests passing. That's pretty powerful. Now, I try to use TDD. I wrote the Gorilla HTTP package in this style, and it was wonderful. I knew exactly what I wanted to implement. I'd written a few HTTP libraries before, so I knew the general shape. And it meant that, so I would write a test case, write the function, add some more test cases, improve the function, add some more test cases, done. And what it meant was, when I got to the end of this, I had a fully working client, it was fully tested, and it was all I needed to do. One of the pet peeves that I have on teams of software engineers that I work with is when you're around in stand-up and someone says, tell me about have you finished adding the bug, or have you finished fixing the bug, or adding the feature, and they say, oh yes, I've done that. Oh, but I just need to write the tests. Writing in TDD style means that when you've finished implementing the code, you've also finished writing all the tests. You are done. The problem was when I didn't know what I was doing, when I was using code to explore the problem, when I was writing code to do a spike or explore the problem space. TDD is really expensive. But if I make a mistake and I need to backtrack and go in another direction, I need to change the tests to undo what I did, and then change the code to follow the tests. And then I have to change the tests again to point in the new direction, and then change the code again to go in the new direction. And so that meant that working in this style, exploring with TDD, was at least twice as expensive as not writing tests. And it got worse. If I wanted to refactor a bigger function or a bigger part of the application, the cost of fixing those tests was hours of work for a tiny change. And I was deeply concerned about the fact that I was rewriting my tests all the time. I mean, changing covered code is safe. You have the test to protect you. But if you change the tests all the time, who is going to protect you? And there's always a risk that the easiest way to get all your tests passing is just to delete them all. So writing tests as I developed a piece of software was a lot of unnecessary work. Changing the tests all the time felt like I was cheating. It felt like I was doing TDD wrong. And then one day I came across this amazing presentation by an English gentleman called Ian Cooper. It's called TDD, Where Did It All Go Wrong? I really recommend this presentation. I've got a link at the end to it. And it contains a lot more wisdom than just the two things that I'm going to tell you today. But those things I'm going to tell you are: the first piece of advice that Ian had was that the system under test, the unit, this is what we mean when we say unit test. It's the system under test, the unit of testing, is not the class. Now, Ian's a .NET developer, so he thinks in classes. We're Go programmers. We have different words. But this idea of what is the unit that we're testing really stuck with me. We can explore this by looking at any language. So if we say, what is the unit of code in a C program? Does anyone want to take a guess? Yes, correct. The unit is a function because, well, all you have in C is functions. So you're going to test at the function level. The next question might be, well, what is the unit in a Java program? I heard someone say class. Yes, this was the point of Ian's talk, that it is not the class. The unit is not the class. But traditional, especially Java testing, we have been taught one Java class, one test class, always one-to-one. So this led me to thinking, what is the unit of code for a Go program? What is the unit that we should test? And this is the question I was thinking about. And it reminded me of something that I'd said at a keynote in India a long time ago, where I was really thinking about how Go and the Unix philosophy. And I said that Go packages embody the spirit of Unix. Go packages interact with each other via interfaces. And most importantly, programs are composed. We compose programs in Go by combining packages together. So, approaching this from Ian Cooper's argument and the realization that the unit of code in Go is not the type or the class or the method or the function. The unit of software in Go is the package. So this is what we should test, not functions, packages. The second takeaway from Ian's talk is that we should be testing the behavior of that unit, not its implementation. And to an external observer, to somebody else using your package, they cannot observe the behavior of the code that you've written unless you expose it publicly, unless it's part of the public API. Anything which is not exposed by the public API is, by inference, and implementation detail. So, we should test our packages via their public API. Now, even if you disagree with me about TDD, I'm pretty sure that you'll agree with me that the public API of your package says, this is what I do, not this is how I do it. This is what the public API of your package says. So when you have new behavior that you want to guarantee, when you add new functionality to that package, you should write a test for its behavior. And you should assert that you've tested all the behavior you expect, because as we're all programmers in this room, you know that people can depend on anything that they can observe, even if it was intentional, even if it wasn't. So now we know what to test. Let's step back just a little bit and talk about how to test again. You've probably figured out that the big idea here is the unit of code in Go is the package. You only need to test the behavior of your packages that can be observed. If people cannot observe it, usually because it's not part of the public API, you do not need to test it. Not you do not need to, but you cannot. If I can't observe it from outside, how can I even see it to test? Code coverage is your guide here. Code coverage is going to give you these answers. It's going to tell you when there are branches that you can't get to from the public API. Maybe you might consider deleting them. They'll certainly give you higher coverage. When you refactor, coverage is going to tell you where you need to add tests. If you refactor your package and your coverage goes down, you have exposed new branches to the outside world. You have exposed new behavior that you have not guaranteed, that is incidental, but is still visible from the outside world. And the opposite, if you have high coverage, consider adding things like fuzz testing to check that you've actually covered all the edge cases, to really test the robustness of your public API. So we talked about how to test, we talked about what to test, we came back and talked about how to test again. The last thing I want to finish on is the question of why. Why should we write tests? Now, I'm sure that none of you in this room think that software should not be delivered without testing it first. Pretty sure we agree on that. Even if that was true, your customers are going to test it, even if you don't. Well, they're certainly going to use your software. That's what they bought it for. And so if nothing else, you want to discover issues before your customers do. You want to make sure that you're not embarrassed by that. And as a matter of professional pride, you want to make sure that the code that you deliver works as you said it does. So if we agree that software should be tested, the question is more, who should do that testing? I argue to you that the majority of testing should be done by development groups. All of us here, all the people in this room. Moreover, this testing should be automated. So the majority of that testing are going to be unit tests that you run all the time. Certainly as part of CI on your machine. Now, to be very, very clear, I am not saying that you shouldn't write other kinds of tests, that you shouldn't write integration tests or end-to-end tests or all-up functional unit end-to-end tests. And I'm also not saying that you shouldn't have QA engineers, that you shouldn't have integration test engineers. But in saying that, I'm prepared to make a small bet. I'm willing to bet you that nobody in this room considers themselves to be in a pure quality assurance role. If you say your job, if you believe that your job is as a tester, would you please put your hand up? Not one hand. That's fine. That's fine. That's totally okay. So I think that makes my point. This room is full of representatives from China's biggest software companies. But all of you here are in software engineering or SRE roles. None of you consider yourselves as test engineers. Now, going back 20 years, in the 90s, it was reasonable that you would, for every software engineer, you would have 1 to 2 QA engineers working with them, testing their code. Those days are pretty much gone. Now, it's all automated testing, it's all CI, it's all pre-commit check-ins. So if the answer is that all of us, the individual contributors, are expected to test the software we write, why do we need to automate it? Why do we need to write automated tests? Why is a manual test plan not good enough? And the reason that a manual test software or test verification is that it does not scale. As the number of manual tests grows, it takes longer to run them because they have to be done by people at the speed that people go at. It's also that most of the time, you would expect that 99% of those manual tests will pass. So there's a strong preference to cut down the time testing takes by only testing things that you think have changed. Manual testing is expensive, it's boring, people are not good at doing boring, repetitive work. And what this means for all of us is that your first response before you sit down to change the code, whether it's a new feature or a bug, is that you need to write a unit test to prove that when you've implemented that feature or fixed that bug, it actually does what you say. Then, you've fixed the bug or you've delivered the feature, you have a test to prove that the new behavior that you added or repaired works, and that's now included with your check-in. So that means it can never regress again. If somebody removes that functionality or breaks the fix that you add, the test that you wrote will fail. Tests are a critical component of making sure you can always ship your software. As a development team, you are judged on how you deliver working software to your businesses. I'm sorry, they don't care about ping pong tables or LaCroix or the latest MacBook. What the business wants from you is working software. And that means that your superpower is that the business can come to you at any day of the week and say, we need to do a release right now. You say, sure, done. You push the release button. Because nothing is going to reduce your standing with the rest of the business owners if they say to you, we need to release today, and you say, oh, it's not a good time, we're in the middle of a refactor, it'll be, we hope, a few weeks. You never want to be in that situation. So, I'm not saying you can't refactor, but I'm saying at every stage along that, you have to do it in a way that all your tests pass. And the TDD doctrine of always being able to release, because if there is a broken test, it's just Control-Z or revert one commit, is really powerful here. We talked earlier that tests, you want to test the behavior of your APIs, not their implementation. Your tests are the contract about what your software does. When people come to me and they have a question about how my product works, the first thing I do is look to see, is there a test case that is checking that the thing that they want to do is something that I've thought of. And lastly, and this is the biggest one, for programmers working on a piece of code that has been through many hands, you all work on big teams where you have products that were there before you started and will be there after you leave. The tests are the thing that is going to help you, give you confidence that you can change that software. Your tests are going to give you confidence that you can refactor that software, even if you weren't the expert that wrote it. The tests are going to guarantee that you haven't changed the behavior. So let's wrap up. You should write tests. I don't think that's controversial. You should write tests at the same time as you write your code. I think this is very important. I hope I've convinced you that this is a useful thing. Each Go package is a self-contained unit. They're not friends with others. They shouldn't have close relationships with each other. They should be self-contained, and all you can observe about them is their public API. And your tests should lock that in by asserting this observable behavior. If you're testing some implementation detail that leaks out of your package, that's a mistake. And lastly, you should design your packages around their behavior. You should always be thinking, what does this package do? Never think, how does this package do its thing? Say, what is it supposed to do? And that starts with simple things like the name of a package. What does the HTTP package do? Well, I'm pretty sure it does HTTP things. What does the database package do? Well, I'm pretty sure it does DB things. So you can start thinking about the design of your packages by thinking about what do they do. And with that, thank you very much for your time. Thank you so much.